Friends, we will continue to discuss more concepts related to fire resistant design as applicable to offshore platforms. We have understood in the last set of lectures characteristics of fire, different types of fire. We will also deal with varieties of types of fire in this module in the next lecture as well. We have also understood various mechanical properties and characteristics of material at elevated temperature. We have realized that understanding the yield strength and Young's modulus is important at different strain rate, which should be compatible with the rate of loading as far as blast resistance and explosions are concerned. We have understood that fire resistant design in general should be based upon deformation control and not essentially on strength control. We will talk about the design procedures as well as we continue ahead with the set of lectures. In this lecture now we will discuss about the fire resistant design. We will have an overview of the whole process. Friends, let us try to ask a question: what are essential functions of an offshore platform and therefore, why a fire resistant design is necessary? Let us ask this question. We already know that offshore facilities are essentially constructed to explore, produce, process and store hydrocarbons. Offshore facilities are large, extensive, special and unique in terms of their geometry, function and even type of structural system. So, asset protection is very important in offshore platforms. So, my design procedures should enable absolute safety of the asset, so that in case of any untoward incidents, even accidentally, the asset protection plays a very important role in the whole design philosophy, because offshore structures and offshore platforms are commissioned at a very high price and they are inevitable and very crucial for nationals' economical growth. Therefore, we cannot take a chance of capsizing or losing the offshore asset just because accidentally a fire or explosion occurs in the platform because of risk involved in the process of production of hydrocarbons. So, therefore, we have realized that offshore platforms deal with flammable materials. Let us say hydrocarbons. Therefore, one can say that offshore platforms are generally under high risk of fire and explosion. Let us look into a variety of operation which takes place in offshore platform. So, this will give a hint for us to realize the degree of risk involved in terms of fire and explosion in offshore facilities. Separation, water injection, high pressure combustion, sea water deaeration, local and main electrical functions and accommodation, let us say living, etc. Though all of them do not originate or do not promote or do not promote fire and explosion, but safety in terms of asset management and human resource in all segments of the plant operation becomes very vital. Therefore, safety against fire and explosion is important. Now, the question comes, why fire resistant design is complicated? The answer is very simple. The design process is not complicated, but the layout of the plant to which the guarantee against fire resistance is complex. So, it is actually the layout, because most of the modules on the top side are located in a congested manner. Let us say, to make it more decent, we say it is laid out in a compact manner. For me, as a structural engineer, I would say that compactness in terms of geometric layout is a structural congestion. Therefore, proximity of spread of fire or blast waves from one unit to the adjacent is very high. Further, the layout is also complicated in terms of congested network of pipelines, electric mains, water mains, etc. All of them together makes the design layout highly complex in terms of fire resistance, because as we understand, fire or explosion is a short time phenomena which dies down or decays with passage of time, what we call as TD. Propagation of the waves and type of fire, like for example, fireball, etc., all depends on the layout of the crucial elements or the members that need to be protected against fire. For example, if you are able to lay out the mechanical equipments and the living quarters far away from the hot spots which are probable to have fire or explosion, then the asset damage can be as minimum as possible. But unfortunately, in a given layout of an offshore topside, we do not have this liberty of spreading these facilities far away, because all of them need to be assembled and commissioned at the most compact space available on the top side. Therefore, the level of risk in such conditions is high due to the following reasons. 1. Facilities, equipments, and even the process design are unique. Therefore, they need to be protected. 2. Recreating the facility or retrofitting the damaged platform is one very expensive and practically not worthy, because most of the fire accidents will result in high degree of catastrophe. Both to human and equipments. The third point could be, we all do agree that offshore platforms operate in a remote and harsh environment which do not have any ancillary support of firefighting etc. on demand. Hence, the risk involved in offshore platforms, especially related to fire and explosion, is on a very high scale. Now, let us try to list the potential risks in offshore platforms. The potential risks include blowouts, riser and process leak, of course, fire and explosion, vessel collision causing serious impact, helicopter accidents, impact caused because of dropped objects from the crane, structural failure of members due to unwarranted environmental loads, which we have been seeing through and through in this course as special loads, and of course, a whole or complete capsizing of the platform. So, interestingly, there are large levels and variations in the risks involved in offshore platforms, but one can see here that there are wide variety of potential risks in offshore platform as listed on the screen just now. Out of which, let us pick up fire risk. It is evident from the literature that about 70% of the accidents occurred in offshore facilities are due to hydrocarbon explosion and fire. It is also seen that their consequences were very serious. It affected health, safety and also resulted in environmental disruption, or let us say environmental pollution. So, apart from the asset loss, due to fire and explosion, you also end up in paying penalty towards loss of personal health, challenging safety of the whole operation, which can invoke legal complications on the existence of the facility, and of course, you have to also pay on a societal obligation towards the environmental loss caused because of the accidents. So, it is very vital and important that platforms must be designed to encounter the risks which are arised from fire and explosion. Therefore, one can say that possibility of fire and explosion in offshore facilities are very high. Therefore, it is one of the major concern for the designers to make the offshore system or offshore structure fire resistant. Adding to this, if the platform is dealing with, if the platform is dealing with liquefied natural gas, then the potential risk due to fire and explosion is further severe. That is a very important point. It is due to its physical and chemical conditions of LNG, which is different from other liquid hydrocarbons. But let us make a statement here. Under the given embracement of the complexities involved in layout, an offshore platform has various complexities. Let us see what are they. A congested layout, I can even say, to be very decent, a compact layout, close network, close in sense high proximity of pipelines, electric cables, water mains, etc., which is again a complexity. Third, working in remote and harsh environment. 4, dealing with exploration and production of very high flammable mixture. Non-support systems in case of emergency, very high capital investment and very long process of commissioning one another new facility, what we call as the downtime. All these factors will make an offshore asset or a platform to remain very complex. Therefore, under the given list of complexities, it is important to note that an offshore facility or an offshore platform can never be designed to remain completely safe. then what do we do actually? But by intelligent design, one can improve the degree of inherent safety. So, what are the steps involved in doing this? 1, optimum design and layout of equipments, field configurations, operational features and fire resistance, in fact including explosion or blast resistance, because we do not include them as separate. Blast and explosion resistance are inherent part of fire resistance. So, what do we achieve by ensuring this? That is a very interesting question. What do we achieve by ensuring high or at least satisfactory level of inherent safety? We as designers make the platform to be as low as reasonably practical. So, the risk is reduced to alarm level, plus please understand risk is not and in fact cannot eliminated completely. So, offshore platforms are generally designed with presence of risk. So, what do we do as a designer? We only minimize the loss or damage in case of fire. So, we said that the important source which challenges the potential existence of a platform in case of production, exploration, storage and processing of hydrocarbon, because hydrocarbons are highly flammable mixture. Now, let us talk about the properties of hydrocarbon alone. Hydrocarbons can explode through ignition source. When in the presence of oxygen. Hence, temperature rise during such explosion is almost instantaneous. In the presence of oxygen, combustion takes place, Therefore, hydrocarbons result in blast or rapid increase in pressure. That results to explosion or fire. So, therefore, let us now try to understand the characteristics of fire. Fire is actually a combustible vapor or gas that combines with oxygen in the combustion process. And results in the following. It results in light, results in extensive heat, mostly it is exothermal, and flame. Then let us ask a question, what are the primary concerns of fire analysis? The primary concerns could be the impact caused by fire due to overpressure is results from explosion, which we have been discussing in the earlier lectures. The second could be effect of material characteristics at elevated temperature, which we also discussed in the last set of lectures. We can simply make a layout indicating the cause of fire. Let us say release of a flammable mixture happens, let us say by mistake, it is an accident. This can result in three ways. It can cause no ignition. So, in that case we are very lucky. It can cause immediate ignition, which is quite common, it will result in fire. It can again cause flammable air fuel cloud. This is more dangerous. This is more dangerous because this will result in ignition, which is a delayed ignition, and this can result in further gas explosion, which can cause serious damages. One such example could be Blevy, which is boiling liquid expanding vapor explosion. Let us try to ask a question, learning lessons from accidents. Let us say focus only on fire accident. When we talk about fire accidents offshore assets, the foremost lesson which is being communicated to all offshore engineers is a very classical example of Piper Alpha. Piper Alpha accident occurred in July 6th, 1998 in the North Sea. Piper Alpha is one of the largest oil production system, which is actually fixed platform. We already seen the types of offshore platforms earlier in initial lectures. Fire and explosion occurred. The consequences are about 167 people were killed. The financial loss was estimated to be close to 3.4 billion US dollars then at that time in 1998. Now that it is different. So, people did post analysis of this accident, they did detailed studies of the reasons why such accident had occurred. So, here before we look into that, we must understand that the consequences caused by this accident were of a very high severity. Risk is actually a product of probability of occurrence into consequence. Since the consequence of this is very high, one can say that even though the probability of occurrence of such accidents are very minimum, very rare, but the risk is of a very high order, because you can see the consequences caused by this single accident is enormous. So, the post aftermath investigations concluded that accident occurred due to human error in operation and let us say I should say maintenance. The second was faulty design of the platform. Now, the faulty design can be could be a wrong or highly congested layout, wrong positioning, or planning of facilities on the top side. So, friends, it is very interesting, the whole analogy of planning the topside facility is dealt in detail in brace called feed, which expands for front end engineering design. So, there is a separate brace of team, the feed team, which essentially looks into only an intelligent, non-compromising, but compact layout of various facilities horizontally and vertically in a given platform topside alone. So, feed was not effectively done. So, faulty design could be due to this, and of course, it can also be due to wrong choice of material, because the material could not sustain its intended response behavior at elevated temperatures, which resulted in a permanent deformation at a very high strain rate, and that could have resulted in collapse, or it could have added to the complication arose because of the fire accident. So, friends, one can easily see that the consequences, apart from being very severe, one could have avoided them in terms of at least minimize them if the factors of these can be taken care of properly, which is actually the fire resistant design part. The second example, which can also be highly relevant in the present context, could be the Deepwater Horizon. Deepwater Horizon is a semi-submersible MODU, mobile offshore drilling unit. The accident occurred on April 20th, 2010 in Gulf of Mexico. It resulted in fire and explosion, which led to loss of asset. It also resulted in capsizing of the vessel, which is a complete destruction. It also resulted in oil outflow, which affected the environmental characteristics of sea water, which was also a penable or a punishable offence to the company. So, here also once again the consequences are multi-complex. It has both human and environmental impact. It also resulted in a very serious financial loss of asset. The diagnosis of this event show that reasons for explosion are a small diameter hole which is a vent got obstructed due to dirt circulation. This happened in the casing string of the drilling riser. The second diagnosis was reported to be the valves which are supposed to prevent cement backflow did not close on demand. So, misfunctional operation. It also said there was an inadequate cementing in the drilling casing. It also was noticed that the pressure test conducted on the drilling unit was wrongly interpreted. It is also noticed that the rising oil and gas content in the riser was not monitored. So, one can see here that most of the aftermath conclusions show that more or less they are operational difficulties, but they are also coupled with the wrong design. So, design plays a very important role in ensuring minimum loss to the asset even under such catastrophic accidents like fire and explosions. So, friends, in this lecture we are trying to understand the necessity of fire resistant design of offshore platforms. We have also understood that offshore platforms deal with processes which are highly risky. We can only control the risk to an acceptable level like alarp level, but we cannot attempt to mitigate the risk completely. So, fire resistant design will be helpful. Is helpful in minimizing the loss. It cannot mitigate the loss. Please understand. Thank you very much.